Okay, so in the last class we were looking at, or we completed looking at the Fourier series, and the last bit that we talked about in the Fourier series was the so-called discrete Fourier series. And the reason why we talked about this, even though you're not going to program this in this particular course, is to appreciate the fact that when you're going to take the Fourier transform, if you've got a continuous function, then you can simply extend the domain from minus infinity to plus infinity. And since the function is continuous, you still can resolve the components of the function in any of the basis functions that we talked about. Okay, so that's something that is the good point about a continuous function. But most real life functions are usually discrete in the sense that you know the function at a few points, and maybe you try to connect them with some kind of lines. But it's not necessary that those lines are correct, and therefore you are going to incur some errors, and we call that, for the Fourier series, the projections of the function on the basis functions were represented by that Cn, and for the Fourier series in the complex plane, we said that the Cn was given by 1 by 2L minus L to plus L fx e to the I n pi x by cap L. Okay. And we did some amount of algebra then, and we said that we would replace this integral by some kind of a summation, and once you do some algebra, there is that cap n in red that I'm showing, and because that's a constant, usually one does not compute it, although it's there. And then in subsequent algebra, you will see that that's not there, even in the slides here. And we did a little more algebra, and what we came up with is a bunch of linear equations that can be solved. And if you are going to define omega as e to the minus I 2 pi by n, then you are going to get a matrix equation that looks something like that. You can very easily solve it, and you're going to get what the values of C's are. And C's, once again, are going to be the projections on the unit basis functions, or if you are looking at signals, then it's the resolution of the compound signal into its components. Okay. But one big caveat in all of this is that you're only going to be able to get so many C's, and even though you may say that for a continuous function, I could extend it from minus infinity to infinity and extract the other or resolve the other frequencies or resolve the other components in the basis function directions. When you have a discrete function, you're not going to be able to do that. Okay, so that's something that one needs to keep in mind. The electrical guys do a lot more about this. We are going to close our discussion on the Fourier series on this note. We have kind of gotten an appreciation of what the Fourier series is and what the various components represent, and then what the Fourier transform is, and how one can resolve a decent number of components in it. And finally, something about the so-called discrete Fourier transform, and what that is going to give us. And I had shown you a couple of ways in which these equations are solved, and I used Scilab as the vehicle and showed you that all these algorithms which are going to compute the Fourier transform are going to spit out a bunch of C's in the complex domain, and you need to process them a little bit based on what we have seen in class, so that you are going to be able to construct the function back the way it is. Okay. So with that, we close our discussion on the, okay, one last thing is that matrix that you saw has got these 2 pi I by n's, and people call them the roots of unity. And normally one would say that the root of unity is unity itself, but in the complex domain, they are different. And this is just an aside to just appreciate that in the complex domain, you are going to get the roots of unity from that unit circle in the complex plane. Okay, so with that, we close our discussion on the Fourier series, and we start looking at partial differential equations, which is the next major topic that we are going to be looking at in this particular course. So we looked at ordinary differential equations, and what we said was that in ordinary differential equations, the dependent variable was a function of just one independent variable, and so we represented it as d of the dependent variable. Okay, and so dy dt was what we were writing, and now we are saying that y, or whatever the dependent variable is going to be a function of more than one independent variable, and therefore we'll change the notation a little bit and convert that d into a del. The major equations that we see in this particular course are the heat diffusion equation, the wave equation, and the Laplace equation. Okay, we'll do things in 1D in some amount of detail, in 2D in a little less detail, and in higher dimension in possibly no detail at all. Okay. So the basic algebra is what we are going to be looking at, and this is algebra intense, and much of what those the so-called Wolfram alpha, etc., are usually not going to be giving you solutions to these partial differential equations. Okay. Not the standard ones that are available. Okay. So in this particular course, we are going to be using separation of variables method quite a bit, and it does a decent job in quite a large number of situations, and we will restrict ourselves to the situations where the separation of variables works. And towards the end of our discussion, we'll also look at the Laplace transform and the Fourier transform methodologies to go ahead and solve these partial differential equations. We're not going to spend too much time on it because the solutions are very nice and elegant, and you get the solutions in the Laplace domain or the Fourier domain, but even these standard canned software has trouble in inverting that back into the time domain. So we're not interested in the S domain, we don't live in the S domain, we live in the T domain. So even if you have a very elegant solution to a situation in the S domain or in the omega domain, it's not something that's very useful unless you're going to be able to convert it back into the time domain. Okay. But we are going to be spending a little bit time on these methodologies also. Okay. All right. So let us formally now start with the so-called heat diffusion equation. And what we have is del u del t is going to be equal to alpha del square u del x square. This is the standard heat diffusion equation in one dimension, and this guy is first order in time and second order in x, and therefore we need three conditions. Okay, so how many conditions on time do we have, or how many conditions on space would we have? We now are going to look at the domain. So you need to now necessarily look at these domains. So let us just say that we've got an x, this is the x, and at time t equal to 0, there is some profile for u. So that's the domain that we have. We are not going to derive this heat diffusion equation. That's not the purpose of this particular course. We'll assume that that exists, and in another particular course you may go ahead and derive it and see that something like that is going to show up. In this course we are only interested in trying to get what the solution of this equation looks like. So u is the dependent variable, t is the independent variable, x is the independent variable. We have an equation that is second order in x, first order in time. So we need two equations or two conditions on x. So we'll say x, u at x equal to 0 is some function of x. So at all x at time t equal to 0, that's my first condition, and that takes care of this guy here. And then you have u is going to be at, let us say, L and at all time is equal to 0, and u at x equal to 0 and at all time also equal to 0 in this particular case. We're going to relax this as we move along a little bit. Okay, not too much, but a little bit we are going to relax this. Analytical solutions are available for a very restricted class of problems. That's why I say we are not going to relax that too much. But even for these simple situations, the solution is not that pretty, if you will. Okay, so this is some kind of a rod, and initially there is a temperature distribution, and at all times at x equal to 0, the distribution has got whatever that dependent variable is going to be equal to 0, and at x equal to L also that number is going to be equal to 0. So physically one can think about a rod which has got an initial temperature distribution, some temperature at this end, some temperature at this end, and some temperature as the initial condition. And what you're interested in is what is happening as time progresses to the temperature at various locations. Okay. So that's just to give you a physical feel, but if you don't appreciate that, that's perfectly fine. We are just going to do some math and nothing more than that. All right, so the first thing that we do here is to say that the equation is going to be such that the variables, the independent variables I have are x and t. X usually is space, t usually is time. So I have got a variation in space, a variation in time, and these two variations are separable. So I can separate the influence of time and the influence of space in this particular equation here. Okay. Does not happen in all, but in this particular case, it is likely to happen. That's why we are even looking at it. So we say now u is equal to x of x times. So u is equal to x of x times t of t. So what would I get for partial u partial t? What would partial u partial t become? U is x t. So what is del u del t? X is a function of x, so it's going to come out, and t is there, and now this is a total derivative. Right? So t is a function of t only, x is a function of x only. So if x is a function of x only, it can come out of here, and because this variable t is a function of little t only, so this becomes a total derivative. So this guy is equal to alpha. Alpha is some constant. As of now, what that constant physically means, we don't want to worry about. Alpha is some constant, and we'll just drag it along. So alpha del square u del x square. So what is del square u del x square? X double dash times t. Okay. So all that we are doing is brute force putting the variable u equal to x times t, and then we are just opening this guy up by pushing it into the governing equation, which is here. Now, we have seen when we were looking at the ordinary differential equations that the boundary conditions or the initial conditions are important. So we need to push these guys in this also and see if I'm going to be able to make some sense out of it. Okay. So let us look at this guy here, u at L and t. So x at L and t, this is equal to what? U at L and t is equal to xt. So x is a function of x only, so x at L, and t is a function of t only, so this is at 0. Correct? This is given to be equal to 0 for me. Okay. This is at all times. Okay. Okay. So what can I say by looking at that expression there? Can I say anything? Remember, I want to separate the variables. Okay, okay, let's first get here then. I want to separate these two guys, and we have written up our governing equation like that. So you can write this equation as t prime upon t alpha t is x double prime upon x. Okay. What can this be equal to? T prime upon t is equal to x double prime upon x. This guy is a function of t only. This guy is a function of x only. So if at all these two guys are equal, what can they be equal to? They can only be equal to a constant. Okay. So what we say is, we're going to assume that this constant is going to be lambda square. Okay. Lambda square, because lambda square is always a positive number, and therefore we say that we could either have a plus lambda square or a minus lambda square. Okay. Just so that you have all the bases guarded. Okay. So t prime by t is equal to this. Okay. And now the reason why we say that the variables are separable is kind of coming out clear. So t prime is equal to alpha lambda square t, that's one equation, and x double prime is equal to lambda square times x. Okay. We'll worry about the SIGN of lambda square in 1 minute. Okay. So this is, we have successfully separated the variables in the governing equation, and we have now a ODE or an ODE in T and an ODE in cap X. Okay. So now we know how to solve ODEs, so it's a fairly straight game, it looks like, and it probably is for some time at least. Okay. Now we have got two equations, and now we would like to see what the conditions are. Okay. So this guy here requires one condition, and this guy here requires two conditions. What would be the conditions? What is equal to 0?
X of 0, X of.
Okay, x of 0 is equal to 0 and x of L equal to 0. Why? Cap x of 0 is equal to 0 and cap x at L is equal to 0. Why do we want that? Or how do we want that? Remember, in this case, everything starts looking trivial, but once we start looking at things a little more carefully, one has to be a little careful. Okay. So this guy here is my first condition which I had, which was u at L and T equal to 0, and we translated that to XL and TT equal to 0. Now this implies x of L equal to 0. Why so?
P of P is you don't have, like, and the final function is 0.
So this guy is 0, then also the final function is 0. But you are right. Okay. This guy here is a function of time still. So you are right. Okay. So when you have got T of T equal to 0, it cannot be equal to 0. The only place which this equation is going to be able to get satisfied with is if this guy is equal to 0. Okay. So this guy is equal to 0. Great. Similarly, you can show that this guy also is equal to 0 because I have x of 0 and T of T is equal to 0, which implies x of 0 is equal to 0. Okay. So I have got my two conditions. So I've got x double prime equal to lambda square x, x0 equal to 0, xl equal to 0. Okay. Alright. Now let us see this expression here. So let's get rid of this guy here. Okay. Now what about this condition here? What about T of T equal to 0? X of x, right? So I have got my u is equal to x of x times T of T, this. And now what we are saying is that this is equal to Px, okay? This guy here, time t. Now what can I get for this condition here? Okay, so this does not really give me anything about this here concretely, right? So this guy is a function of x, this guy is a function of x, so I cannot say anything about what T of 0 is, so we'll leave it floating for now. Okay, later on we will come back to it and we are going to see what this is going to be. Alright, so I have got now T of T is equal to this. So what's going to be the solution for this guy? T prime is equal to alpha lambda square T. What is T equal to then? From our original exposure to ODEs, what is the solution for T? Some kind of e raised to the power of, some may be constant, e raised to the power of lambda square T. Pardon me, alpha also is there. Okay, now what we argue is that this guy here is representing, which I just erased a couple of minutes ago, this guy represents a physical problem. Whatever that physical problem may be, it's a physical problem, and there is no limitation on T because we have not put any limitation on T. T can go up to infinity, right, in principle. So if T can go up to infinity, then this function is going to blow up, right? So this cap T, if it blows up, then I don't have a solution. Just to once again bring this example back, I had a rod. The temperature on this side was T1, the temperature on this side was T2. Initial, so this is my rod, temperature is T1 here, temperature is T2 here, and I leave it. Eventually, what is going to happen? T1 equals, okay, let's not worry about the physics, what happens eventually, but the only certain statement that we can make is that this temperature is not going to go to infinity, right? That much we can say. So if this is T1 and this is T2, you said T1 is equal to T2, but what actually will happen is you'll get a straight line profile at the end, okay? But that's another issue altogether. What we can say with certainty, without any hesitation, is that this guy cannot go to infinity, which means it cannot blow up. Okay? So what can I say now? What can I say about this guy? Okay. So far we have said nothing about this lambda square. Okay. We have just said it's a constant, could be a plus constant, it could be a minus constant. So if this guy were a plus lambda square, which is what we have done so far, the solution blows up, and therefore plus lambda square is something that is not acceptable to me as a solution. So that's the argument that we are making. Okay. Now later on we are going to make a similar argument with this function here, although both arguments, one can use any one of them to say that my lambda square has to be always negative. Sorry, the lambda square is always positive. This constant has to be always a negative number. So you will have T equal to some C e to the minus alpha lambda square T. This guy is okay probably, because as T is going to go higher and higher, this guy is going to go down, which is fine. Okay, so from a physical point of view, we are arguing that this lambda square is going to be or the SIGN on this constant is going to be a negative number. Okay, so that's the argument. Okay, so we have argued that. Later on we will take x and argue that still it should be minus of lambda square. So either way you are going to be able to argue that my lambda square or my SIGN on lambda square has to be a negative number. Okay, so that's the argument. Now what about this guy here now? Now we say we are going to go ahead and get a solution for, okay, alright, the other thing that I have not mentioned is what happens if lambda square is 0? That's also a possibility, right? So is 0 acceptable? Lambda square plus lambda square minus lambda square 0. These are the three options that I have for my constant. Is 0 acceptable? What happens if it is 0? In this particular equation that we just wrote, if this guy is 0, what happens? It becomes a constant. Okay. So is constant something that is okay for us? No, because t is a function of time. Right. So if t itself is a constant, then your solution u is a function of x only, and I know the solution cannot be a function purely of x. Right? So therefore u has to be a function of x and t. So lambda equal to 0 is also not acceptable. Okay, so the only possible SIGN for this is a negative lambda square, and we argued based on the t. Later on we'll argue based on x also, but as of now one argument is good enough. So what happens to this now? X double prime is minus of lambda square x. What is the solution for this? What is the solution for this equation? Cos and sine. Okay, so x is going to be equal to a cos lambda x plus b sine lambda x. So that's my solution. This we have done n number of times so far. Okay. So my x, which is a function of x only, is going to be equal to that. Okay. Now I have got my conditions here, x of 0 equal to 0 and x of L equal to 0. So x of 0 equal to 0 implies what? A is equal to 0, right? Because I've got sine 0 is 0, cos 0 is 1, so A becomes equal to 0. So my x becomes equal to sum b sine of lambda x. Okay. So that's one condition taken care of. Okay, the other condition is x of cap L equal to 0. So x of cap L equal to 0 equal to sine lambda L. Now what does that mean? Lambda L is n pi, yes. Okay, so lambda L is n pi. So lambda L is equal to n pi. Okay, so this is what my condition is. So I've got a partial differential equation. We started by saying that my solution is going to be x of x times t of t, and we showed that my t was equal to sum c e to the minus lambda square alpha t. That's what the t came out as, and the x now has come out as, the x is sum b times sine of lambda n L, where lambda n is going to be equal to n pi by L. So I know what my lambda n is, I know what this is, so it looks like I got my solution. Right? So what's my solution? My solution is u is equal to sum tie b sine lambda n L, and lambda I know is n pi by L, so I have got sine n pi by L x, and then e to the power of minus lambda square alpha t. So I have got my lambda as n pi by L, that was that x that was hanging in there, And so u is going to be equal to b sine n pi x and then that. Okay. Now is that my solution? That's my solution, right? Nothing wrong with that. So we have used up two conditions. We had used up this condition, we have used up, this condition we have used up, and now I am left with this condition, and then I am done with my solution. Right? So let us use that condition, which was u. So this is u. So u at all x time t equal to 0 is equal to some px is equal to some b sine n pi x by L, and this guy becomes equal to some constant, so we'll absorb it in that b. So u is equal to this. Now what is this therefore? I've got something called a b here, which unless I know what that b is, I don't know my solution. So how do I get this b? We said, okay, we are going to use the so-called initial condition. We put our p of x here, and then we put this here. Under what conditions will I get a number for b? Under what conditions will I get a number for b? If p of x is known, it's already known. We have said that p of x was known. Tick, 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 some p of x is there. Okay. So, and remember b is some constant. So how do I resolve this issue now? Okay. The problem is, unless this p of x is some kind of a sine n pi x by L, I don't know how to get this b here, right? So if p of x is equal to some sine 2 pi x by L, 3 pi x by L, whatever, I'll be able to get what my b is. But otherwise, I'm not going to be able to get what it is. Okay. So, okay, so p of x is equal to a sub n, some constant b, sine n pi x by L, and this guy we are putting it as equal to 0. So p of x is equal to this, and I don't know now how to proceed. Right? If p of x were sine of something, suppose this were sine of say 2 pi x by L, then I will say I'll put n equal to 2, and then I'll get a b, and I'm happy about it. Okay, or whatever. So, but that's not the situation here. So what's the way out? What is the way out? Remember when we were talking about the Fourier series, we made a remark that, if you have got some function, right, I know what the function is, I can represent it as a series of sines and cosines. And at that time I remarked that it looks pretty stupid to try to say that I know the function and then I'm going to represent it as sines and cosines, right? Why would anybody do that in their right frame of mind? Okay. But at that time I said that, well, sometimes there are situations where one wants to do it. And here is one situation. I would like to say that this guy p of x, right, some function it is, I'm going to represent it in terms of sines and cosines using my Fourier series. What is the advantage it gives me? At least it looks like the right hand side. Okay. So what was the Fourier's? Okay. Now this guy here, we had just said that this was my domain and this was this. Okay. So this is p of x. Okay. Now I'm going to use my Fourier series to represent this in terms of some sines and cosines. Okay. How do I do that? This guy here is just available to me at some particular L. Okay. Fourier series is for an infinitely large domain. It's a periodic thing. This is not periodic. So what do? I brute force make it periodic. Okay. And then I'm going to check, or I'm going to use only this part here. Okay. And how do I want to make it periodic? Do I want to use even functions or odd functions? Odd functions. Why? Because? Correct. Okay. So the right hand side is sine n pi x by L, and we know that if there was a general Fourier series, this was n pi x by L. Okay. So the right hand side is sines, so I would like to go ahead and represent this as a Fourier series which is going to be an odd function, which means that I'm going to extend this guy like this and then let it go to infinity. But I'm going to use the function only between 0 and L. I still have my function, not a big deal. Okay, so that's what one can do. Okay, so that's what, let us say we do that. Okay, this guy here, therefore, we will write it as sine of Cn sine n pi x by L. Okay, that's a possibility. But now this guy is an infinite series, and this guy is something which appears to be just one number. So what's the way out? What do you want to do therefore? Right hand side is a summation. So left hand side should also be a summation, right? So can I just brute force make it a summation? Yes. For every n there is a solution. So okay, great. So why is it that you can superimpose? What is the big thing that permits you to use superposition? The differential operator we are using is a linear operator. Okay, it's a linear operator, and therefore we should be able to go ahead and superpose. Okay, so we should be able to go ahead and superpose the solutions. Okay, so let us see what this superposition is all about. So first thing is that I have got this guy here. On the right hand side, I've got a summation sign. So somehow brute force, I want to make that a summation. Okay. So if this guy is a summation, this guy is a summation, then I will just pick out each n and say that I'm going to be able to get what my coefficients are. Okay, that's a possibility. And we therefore say that I'm going to now hypothesize that my solution U is going to be a summation solution. Okay. Just by saying that U is going to be equal to x of x t of t did not seem to work. Fine, no problem. What we say is that U is going to be a summation of a large number of terms which is going to go from 1 to infinity. Now, why does this work? Because this is my equation now. So this is my equation, and let me just open that guy up. Del t of u1 plus u2 plus blah 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 up to un, and then all the way up to infinity, is alpha del square del x square u1 plus u2 plus dot 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 dot. Because that's what that means, right? Okay, so what can I therefore say as far as the equations are concerned? We have our governing equation, and we are saying that the solution is being hypothesized to be equal to a summation of u's, and therefore I have got del u1 del t is alpha del square u1 del x square, right? And then del u2 del t is alpha del square u2 del x square, and then dot 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 dot. So we had one equation, you made it into an infinitely large number of equations. It appears that we have made life difficult for ourselves, but not so. Okay, we'll see why so. But as of now, what we have done is, we had that one equation sitting up there. We hypothesized that the solution is a summation of a large number of solutions, and therefore this guy is like this. Okay? This is where the linearity ends. Okay? But I should also make sure, if I want to get a solution for that, to do what? To make sure that the boundary conditions are also consistent with the original equation. Okay? So I need to make sure that this u1 plus u2 business is also applied to the boundary conditions. So I've got u1 plus u2 plus dot dot dot, right, at x equal to 0 and all time is equal to 0. Right? That was my condition there. U at x equal to 0 and all time equal to 0. So what can I say about the u1 at x equal to 0 and all times? Something we have done in the past while using ODEs. What can I say about it? Can I just say that u1 at x equal to 0 and all time is equal to 0? Can I make such a statement? Why should that be so difficult? I can do anything I want, right? I can call this equal to 10, for example. Right? I can call this 10, I can call this 20, I can call it 0. If I want life to be easy for myself, I'll make it 0. Okay? And then what should I do therefore to be consistent? To be consistent, I should make u2 of 0t equal to 0, u3 of 0t equal to 0, and so on and so forth. So that is important. If you want, you can make this equal to plus 10, make this equal to minus 10, not an issue. Okay? But getting a solution is a problem, right? Because we have already spent enough time trying to get a solution for that. And we know what the solution probably looks like, right? So we say that this is by choice, and this we are going to do n number of times now. Okay? We have done this in the past also, but when we are looking at these partial differential equations, such a choice is going to be made over and over and over again. Okay? So what we have said is, u is a summation and this guy is equal to 0. So this is equal to 0, this is equal to 0, this is equal to 0, dot 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 dot. Okay. What about the next one now? What can I say about the next condition? The next condition is u at L and 0, u1 at L and 0. What is u1 at L and 0? What would be u1 at L and 0? What would I choose, for example? I would choose 0 to make life easy for myself. And I would choose u2 L0 equal to 0 and dot 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 dot. Okay, great. So I had one equation in u, I have n equations in u, but all the conditions appear to be quite similar or they are under control. Okay. What about the last condition, which is u at all times, at all x time t equal to 0 is equal to p of x. Remember, to be consistent, I need u1 at all x and time t equal to 0. At all x time t equal to 0. What would I do here? Dot, 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 dot. If I have this, I am in good condition. Okay. I can go ahead and get my solution. And when do you think we can get a solution, or when did we say we get a solution? When did we say we would get a solution easily? We said that Pn, we said was an sine n pi x by L. Okay, and we said clearly no n will satisfy. If Px is itself a sine function, then it satisfies. So what would be my strategy here to fill these guys? I know one of my solutions is for any of these guys, what was my x? What was my x? B sine n pi x by L, correct? This was my solution for this. And any n was a solution. I can pick any n I want, right? And so, what n's would I pick here? What would I pick here? So that life is easy for me. Ultimately, the bottom line is life has to be easy for me. Okay. Otherwise, all of this is of no use to me. Okay. So, I have got the u1. Suppose I choose this as sine of 1 pi x by L. Would that be okay? I choose this as sine of 2 pi x by L and dot 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 dot. Would that be fine? Because what was my u1 plus u2? This was u1 plus u2 plus dot 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 un. We said was equal to p of x, and then we said I'm going to expand this p of x as being equal to summation of Pn sine n pi x by L, right? So this guy is B1 sine of 1 pi x by L plus B2 sine of 2 pi x by L dot 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 dot. And this is U1 plus U2 plus U3 plus dot dot dot. So all I'm saying is take this guy, make it equal to this. Take this guy, make it equal to this. Right? I can choose whatever I want. Right? So we say that this guy is whatever B1 sine n pi x by L, B2 and dot 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 dot. Now do we know the solution for the original equation? Remember we started with this here. We said if Px, right, is something like sine n pi x by L, I have my solution. Right? And indeed we have made it so. We have made it so. Right? So if my Px, now my Px has been broken up into all of this. From our earlier Fourier series analysis, we know what is B. What was B? B was equal to what? We said that if our, okay. So we'll stop here today. I think mostly it is done. We'll just finish it up on tomorrow afternoon. Thank you very much.